equations directly.
हाँ जी, थोड़ा सा आप स्टार्टिंग में बताओ और उसके बाद आप अपना वाइंड अप करिए. फाइन.
I have 37 slides.
हाँ जी, ये तो ना क्रॉस कर दो,
Slides ही show कर दो.
सामने क्रॉस करो. डू इट फास्ट. फुल स्क्रीन करो. डू इट फुल स्क्रीन. हाँ जी बिल्कुल बिल्कुल. डू इट फास्ट.
Good evening, everyone. First of all, I would like to thank the organizing committee and chairpersons for giving me an opportunity to present my research paper here in this conference. Let me introduce myself. My name is Nikhil Kumar. I am student of MSc Physics first year from SLIET LONGOWAL. As you can see on the screen, my topic of presentation is structural, phase transitional, magnetic and thermo-physical properties of neodymium nitride under high pressure and temperature. A first principle study. This is the outline of my presentation. From the survey of literature, I found that sufficient experimental data is available on neodymium nitride with less theoretical work. Neodymium nitride is used for a variety of technological applications like in the field of spintronics and reactor fuels. Today I am going to be reporting on the results of the study we have carried out. There are some general properties of neodymium metal. It has atomic number 60 with electronic configuration xenon 4 and 4, 6s2. It is bright and having silvery metallic luster. It combines with nitrogen to form a blackish powder neodymium nitride. Now coming to the theory part, Schrödinger wave equation first principle proof. In physics, a calculation is said to be from first principle if it relies on the basic and established laws of nature without any additional assumptions or special models. All the information of a system is contained in system's wave function, and this wave function for a single electron moving in a potential V can be calculated by using Schrödinger wave equation. Here, the first term is kinetic energy, second term is potential energy, and epsilon is the energy eigenvalue. Now, suppose if there is a many electron system, then how can we solve the Schrödinger wave equation? So, the problem extending to the many electron system, Born-Oppenheimer approximation is to be used. According to this Born-Oppenheimer approximation, the wave function of many electron molecule is a function of electron as well as its nuclear coordinates. The motion of electrons and nuclei are coupled. However, nuclei are much heavier than the electrons. Consequently, the nuclei move much slowly than the electrons. So we can differentiate their motions. So using this approximation, the Schrödinger wave equation can be modified as here the additional term is electron-electron repulsion. It is added in this equation. Now coming to density functional theory. In quantum mechanics, the total wave function of a system is depends upon the coordinates of all the electrons present in the system. So the problem is still far too complicated to be exactly solved in practical computation. To overcome this problem, further developments are required to perform the ab initio calculations for the real materials. The DFT provides the framework for these calculations. The Hohenberg and Kohn firstly demonstrated this density functional theory in 1998. They got the Nobel Prize for this discovery. The first conceptual advantage of DFT is the possibility of describing the ground state properties of any material, any real material, in terms of its ground state charge density. Now, here the one-to-one correspondence among the energy and external potential and ground state charge density. There also exists an additional energy term that consists the exchange correlation energy. In a system of many electrons, there are interacting electrons as well as non-interacting electrons. What is exchange correlation energy? How the movement of one electron or energy of one electron varies due to the influence of presence of other electrons in the system. Rather it is adjacent or it is far away from that electron. That is the exchange correlation energy. So the Kumar suggested an easy approach to solve this Schrödinger wave equation. And there VKS is the effective potential containing some potentials, that is Hartree potential and exchange correlation potential. Now we are mainly considering the exchange correlation potential, which is additional.
Show your control. पेपर तो आप पहला के सर उसमें प्रोसीडिंग्स में डालेंगे ना इस चीज़ को, देने को ध्यान रखें क्योंकि इसका कंप्यूटेशनल डिटेल्स वहाँ से
We have systematically computed the structural phase, transitional and magnetic properties of neodymium nitride in two different phases. B1 phase, that is sodium chloride phase, and B2 phase, that is cesium chloride phase. Our calculated value of lattice constant of neodymium nitride is 5.105 angstrom, which has well agreement with the experimental value, that is 5.132 and 5.124 angstroms, that is given in the reference. Neodymium nitride is stable in sodium chloride structure up to 52.95 gigapascal, and it transforms from B1 to B2 phase at 52.96 gigapascal. The obtained magnetic moment for neodymium nitride is 3 magneton, so it is a high integral value. That's why you can say that it is a ferromagnetic compound. The calculations have been performed within density functional theory using full potential method using quasi-harmonic Debye model, implemented in Y2K code and Gibbs code respectively. The generalized gradient approximation has been used to solve the exchange correlation potential and energy. In different Gibbs code, sir, मेरे जो सर गाइड थे ना पहले के पास
So these all experiments were performed by the
no, this is theoretical, all theoretical work.
all it has been done over there.
Yes. The thermal properties like volume optimization, thermal expansion coefficient, Debye temperature, specific heat capacities, and constant volume, pressure, and Lorentzian parameters have been calculated at ambient conditions and at high temperature and pressure. Our calculated value for Debye temperature for neodymium nitride is 413.39 Kelvin at 0 gigapascal pressure and 0 Kelvin temperature, which is in well agreement with the previously reported experimental value, that is 410 Kelvin. So this work can further be extended by implementing these as well as few more properties of other lanthanides. In view of recent experimental success to probe such compounds and their relevance to the field of technology, we believe that our work will not only add to the understanding of such systems but also contribute to the future experiments. These are the references. I would like to thank Dr. Sanjay Kumar Singh, Assistant Professor, Department of Physics, SLIET College, Barnala, for their guidance and support. This work I have also presented in Germany as a Forschung Zentrum Research Center. At last year, I was the youngest participant there to present my work there.
Same working project.
Thank you so much.
Same